Hello students, welcome back. We just completed an example problem on an interval estimation of two sample inference associated to two independent proportions. A long introduction, but basically I'm talking about this example problem. Remember? Here's a visualization. Take the difference of the two proportions, and that goes right in the middle, because that is the best point estimate, the expected value. And then apply the z-analysis, center minus z-score times SC, center plus z-score times SC. Those are the endpoints of the confidence interval. So the key here is the standard error. Z-value comes from 99% in the middle. So 0.5% here, 0.5% there. So the z-score is 2.58, approximately speaking. That's not a problem. The problem is SE, and it follows from this formula. Remember? Now let's do hypothesis testing, and this time we're going to end up with a little bit different SE formula. That can cause a bit of a confusion, but here it is anyway. Okay, let's begin. Here's a basic structure of hypothesis testing. One way to do that is to do it like this. Take the difference between the proportions and compare with 0. And here's another way. Compare just two proportions, pi 1 and pi 2. Oh, by the way, I'm using pi for proportions because population parameters are typically written in Greek. So P for proportion, and that becomes pi for population proportions. And then this one is a difference. So PD is difference of proportion. Pi delta, that is difference of population proportions. I don't like to use pi's for these kind of things in class because it may cause confusion. And this is a bit formal, so in my notebook I use pi. So one way to do that is to take the difference and compare it with 0. Another is to compare directly. Either way it works out. Advantage of this is better visualization. You can draw the normal curve around 0 because you have to do it according to the null hypothesis. Advantage of this format, it's related to this. Somehow we have to calculate the SE, and then SC is under the null hypothesis where the proportions are about the same, so we have to reconcile the proportions P1 and P2 coming from two independent samples. How to recognize that is like this, and that generates the SC formula like that. Does it make sense at this moment? Probably not. So let's go to an example problem. And then we're going to come back and discuss how these are related to this structure of hypotheses. All right. Okay. Let's copy and paste these two. Okay, like this. And then let's go to an example problem. All right, here we go. Please stop the playback and read through. All right, a salesperson for a new manufacturer of cellular phones claims not only that they cost less, but also the defective ratio is not too bad, about the same, basically. But of course, the sample study is telling otherwise, apparently. Salespersons have 15 defective out of 150 checked, and competitors have only 6 defective out of 150. So looks like the new manufacturer cell phone is cheap for a reason. It's cheap because more defective ratio. But then again, is it really true? we have to test with level of significance of 5%, because this could be just an artifact, and with larger sample size, things may differ. We'll see. Now, what is the structure of the hypotheses? One way to do it is to use this convention. The new manufacturer has defective ratio pi, and the competitor's line has defective ratio pi 2, and they're actually the same, about the same, versus no, new manufacturer has higher defective rate. That's the structure that we can think of. Make sense? Another way to do the same thing is to use the difference between the two. Either way, it works out. The second expression is a little bit better in terms of graphical representation, because clearly we are doing this normal analysis, Z analysis, around 0. Now, how about the SE formula? We're going to talk about it a bit later, but before that, we have to check a little bit more about sample statistics. Let's see. The salesperson has defective ratio of 15 out of 150. And that's 0.1, isn't it? 10%. Nothing is accurate in statistics, so let me use approximate equality sign. And then the competitors, 6 out of 150. And that is 6 out of 150. Let's see, 2 out of 50 is 0.4. 0.04, excuse me. So that's from the new manufacturer. And this is coming from the competitor. Okay, all right. And then, of course, what's the difference? What's the difference? And that's 0.06, isn't it? Yeah, again, let me use approximation symbols everywhere. Too much space. Okay, all right. So it looks like this is the best point estimate of the difference of defective ratios. Okay, all right. And then if you have to do some interval estimation, go ahead and do that. You can do it with this. 6% point. That's the observed difference in proportion. And then you can use I don't know, 95% confidence interval, 97% confidence interval, you can do whatever to find those out, just like we did before. And there, SE formula was what SE formula? We had to do this. No. This. P1 and P2, 10% and 4%. Yes, we can do those. But it's different this time. It's hypothesis testing, and we have different SE value. And in this case, we have this kind of picture. So you see, hypothesis testing, null is difference is 0. So you're going to draw the normal picture on 0. And then, as you can see, we got 6% point of difference. So we're going to find out the critical value. What percent point here? So that this probability here is alpha. At 5%, 0.05. Now, once you find your critical value x, then you can go toward your conclusion. Compare that with the difference, 6% point. If this falls here, then too close to null, so you accept the null hypothesis. If it falls there, then too far away from the null, so you reject the null hypothesis. You can do all that if you find the critical value. All right? And what do you compare? Well, the difference. So that is the structure here. But of course, in order to find out that critical value x, you're going to need a standard error. And that is going to be the next headache. But up to now, is everything okay? The structure of null and alternative hypothesis either this way or that way. And the second way is a little bit easier to associate this normal picture because null is the difference is 0, so centered around 0. That was easy. And then the critical value you're looking for, and then compare that with the difference of proportion observed from the sample study. And that was 6% point. So whether it goes here or there, that is the question. All good? All right. Next step is find out the critical value. And for this, you're going to need some work. You see, it's kind of like this. You're going to need z-score as end minus center over SE, and oh boy, we need some work. So that's how you're gonna do. And if you wanna step the playback and then complete it on your own, go ahead and try that. So what is P? X1 plus X2. So 15 plus 6 out of N1 plus N2. What is this? Well, according to the null hypothesis, the proportions are actually about the same. Apparently, this has higher proportion than that, but according to null hypothesis, that's just because of luck. So there should not be any difference one way or the other. So you just consider total defective ratio for all 300 samples here. 150 new manufacturer, 150 competitors. No difference. So put everything together and consider 300 cell phones. And out of those, total 21 are defective. So you just go ahead with 21 out of 300 by adding up those defectives and adding up the samples. Why are we doing this? Because we are under the assumption, the null hypothesis, no difference between population 1 and population 2. So we just put all those together to find out the proportion. And that proportion is 0.07. And P1 minus P over N, but for some strange reason, we have 1 over 150, 1 over 150 instead of 1 over 300. Why? That's something we're going to discuss a bit later after completing this, but one step at a time. Just put everything into that SE formula, P1 minus P, 1 over N1 plus 1 over N2, and do your computation. And what do you get? You get 0.29 something, and that is your SE. So, N minus center over SE turns out to be the z-score associated to 5%, 1.65, so you can find out the critical value. And I think it's better with picture. So z-score is N minus center over SE, which we calculated with the new formula, and that should be z-score associated to 5% here, 1.645. From here you can find out your X value, the critical value. If you do it, the standard error was 0.029 something, so you can calculate it. You're going to get 0.04846 something, as you see here, or as you see in this computation. So you can compare that with observed difference of proportion, which is 6% point, and that falls in the alternative territory, too far away from the null, so we reject the alternative. We reject the null and accept the alternative hypothesis. By the way, what if we use the SC incorrectly? Okay, we just take this. Okay, here. And then what if you just do this? SC is square root of P1 minus P over N. After all, didn't we just claim there's no difference? So out of total sample size of 300. If you do it this way, you're going to get a radically different SC value compared with the one you did correctly. So this formula here the first formula there is wrong. That's for one sample inference. You need the second formula for two sample inference. Looks like everything is revolving around the SC formula. Otherwise the same. We're going to need more explanation in SC formula in a separate video, which we will come back and do in just a moment.